at the end of the lesson. Maybe this day, maybe next, maybe tomorrow, I will send you the link to the video file and you can review this video. Well, I ask the students who connect to our meeting online, do you have any questions?
No, you can share.
No. Okay. And the first topic that we consider today, I consider some mathematical preliminaries with you. And you can look here and look to these questions and maybe switch to this mode when the questions appear one after one. So, in our course, in our lessons, we will discuss about limits. And the first question, do you remember what is a limit? What is the limit of a sequence, or what is the limit of a function?
Yes, sir.
Of course, I don't ask you about the strict mathematical definition, but just how do you interpret this notion, limit? Do you remember? Oh, I'm sorry, the sound is very, very bad. I don't hear. I hear that you tell something, but I don't can't understand.
Okay, so we can say that the limit of a function when x tends to x0, it's equal to f of x0.
Right. And I just I write it on a board. Well, you told me that you have an opportunity to switch between presentation and video, so you can look to the board. First, what is the limit of a sequence? Suppose that we have a sequence of some numbers.
Geometrical sequence or arithmetic sequence?
Arithmetic. Some given some numbers. Some numbers, say A0, A1, A2, and so on. Sequence of the numbers. And what is the limit of a sequence? Of course, you can look to any page in internet or any book. You can just type in Google, search the limit of a sequence, and you can find the page in Wikipedia. What is the limit of a sequence? I try to explain you, maybe not very formally, as a mathematical analysis. So we call the number A star as the limit of a sequence. Then, when there exists some small number, we usually denote this number as epsilon, the Greek letter epsilon, then a n minus a star module smaller than epsilon for any number n greater than some given number n capital. So it means that all the numbers falls into some small vicinity of the given number a star. In this case, we said that a star is a limit of a sequence. Let's consider some examples of sequences that have a limit or doesn't have a limit. Maybe the simplest example of a sequence that has a limit is a constant sequence. For example, the sequence 1, 1, 1, and so on. What is the limit of this sequence? It's 1. It's 1 because all the numbers are 1s. So this sequence has limit 1. The next example, 1, 1 over 2, 1 over 3, and so on, 1 over n, and so on. The next example is 1, 1 over 2, 1 over 3, and so on. What is the limit of the sequence number 2?
1, 2. 1 again.
1?
Yeah.
No. I explain you now.
Zero.
Do you
0.
why 0? Some
It's
other
approach to 0.
yes, these sequence approach to 0, of course, because
When we tend to infinity,
yes,
we tend
because
to 0.
when we take n very large, 1 over n becomes very small, and it means that an that equals to 1 over n, the term n equals to 1 over n, 1 over n minus 0 will be smaller than any given small number. I can take epsilon as, for example, 10 power minus 10, and this value will be smaller. I can take epsilon as 10 power minus 20, and this value can be smaller too, and so on.
Please, sir.
Well, this is two simple examples, and now I can give you example, one more example, also very simple sequence. 1 minus 1, 1 minus 1, 1 minus 1, and so on. So let's consider the sequence 1 minus 1, 1 minus 1, 1 minus 1. What can you say about the limit of such sequence? This sequence doesn't have a limit. Doesn't have a limit. Because
it is
1 minus 1, 1 minus 1, it not approaches to one number.
doesn't converge.
Yes, it doesn't converge to one number. It doesn't converge. Well, and also the same idea of a limit over sequence can be applied to functions, and we can answer the question. Next question: what is the limit of a function? Or, by the way, before we consider this question, before we try to answer this question, let's try to give you a more simple question. What is a function? Because sometimes students cannot answer this simple question. What is a function?
A set of commands, a set of instructions.
Sorry, please repeat.
A set of commands or a set of instructions. In case of mathematics, arithmetic operations, a set of arithmetic operations, or a set of operations in general, or a system through which you pass values to obtain a certain result.
As far as I understand your answer, it's yes, it's more or less it's correct that the function.
Yeah, I can give two definitions. The first definition, you can say that a function it's injection and surjection.
No.
No?
Injection is not related to. Yeah, the function in general work. Again, I don't ask you about the strict mathematical.
Or it's an application.
Definition.
It's an application which it's a domain.
Yes. It's, we have some x as input, and we have a rule how to compute.
Yeah, result.
How to compute the result. And this rule, the rule of transformation of input x to output y, in mathematics we call a function.
Yeah.
So some correspondence between in our case, between real numbers. We have one real number, x, and a rule, f of x, that converts it to another real number. This transformation from real number to real number, so we have y equals to f of x. So the rule f that transforms x to y. And if we consider a sequence an or sequence xn that converts to x, suppose that we consider a sequence xn that converts to x star, then we can consider the sequence of function values f of xn, and if this sequence of the function values converges to some number y star, in this case this number is called limit of a function. Limit of a function. Using this notion, the notion of limit, we can answer or try to answer the next question. What function is called continuous? Because continuity of a function is a very important property, and we will use it very often. So how you understand what function is called continuous?
Yeah, the function is called continuous, or is continuous on interval. In certain interval, if every real of this interval has an image to this function.
I think no.
Really?
Every
real of this interval
has
image to this. Yeah.
It's meant this function is defined. You tell me that the function is defined on this interval. We can compute the image.
Yeah, every image of that interval.
Yes,
every.
but in this case, this function, even in this case, the function can be discontinuous. I'll give you an example. I'll give you an example now.
If there is only one result for specific x value, and these results are not that far away in between.
One result for one x.
Yes. And the results should be like not gap in between when x change.
Again, I don't ask about the strict mathematical definition. Maybe informal definition that students usually tell is that the graph of the function is without gems.
Yeah.
Of course, it's not mathematical definition, but it's an explanation. What function is discontinuous? The function with a gem.
Yeah.
And the function without gems is continuous.
Yeah.
But let's consider some examples. Very simple function. y equals to x squared. Y equals to x squared. Of course, you know this function. Let me draw a graph of this function. Yes, it's parabola. Something like this. And of course, this function is continuous. Because this function, the graph of the function, doesn't have any gems. Let's consider another function. Y equals to 1 over x. Y equals to 1 over x. What is the graph of the function number 2? It looks like this. You see that when x equals to 0, this function is not defined. Yeah. The function is not defined. And the graph of this function, like interval, they look like this. And if we consider the interval that contains 0, for example, from -1 to 1, so x is from -1 to 1. In this interval, the graph of the function has a gem. And we can say that the function 1 over x is not continuous on the interval from -1 to 1. But if I consider the same function but different interval, for example, x from 1 to 2, this interval, on the interval from 1 to 2, this function is continuous.
Yeah.
No point of discontinuity. Okay. Now, let me show you one more example, maybe.
So
This function is not so simple like y equals to x squared. Let's consider the function y equals to 1 if x is greater or equals to 0 and -1 when x is smaller than 0. What will be the graph of this function? This function
horizontal.
The function is 1 when x is greater than 0
Horizontal.
and the function equals to -1. But this point is not included. This point is not included because this inequality
Strictly.
is straight.
Yeah.
And you see that this function is defined at every point. Even at the point x equals to 0. At the x equals to 0, the value is 1. But if the x is below 0, the value is -1. So again, at the point 0, we have a jump. So this function is not continuous too. Well, but how to give a definition of of continuous function without notion of without graphs? Very simple. If we know what is the limit, I can say that the function is called continuous when the limit from the right
And the left are the same.
Yes. When the limit from the right and limit from the left are the same.
Yeah.
In this case, this point is not defined, but the limit from the left equals to -1. The limit from the right equals to 1.
Yeah.
And usually, in computer and mathematics, in our course, we will work only with continuous functions. We will use only continuous functions because in real life, yes, sometimes we have discontinuous functions, but usually all the functions are continuous. So we will consider only continuous functions. The limit from the left equals to the limit from the right. Okay. Of course, we will review these mathematical preliminaries very quickly, because I think you consider it on different subjects like mathematical analysis and algebra. By the way, before we continue and before we consider the next question, I ask all of the students who connect to our meeting online also what types of the functions do you remember? Because all the functions can be divided into several classes that has some specific names, the class of the functions. What?
Polynomial function.
Excellent. Very good example. Polynomials. Polynomial functions. And x squared is also a particular case of polynomial. So before we go to the next question, before we consider next question, let me write here some classes of functions, and these classes also are very important, and we will use it maybe at every lesson. Polynomials, we will use it very often. How to write a polynomial in general?
X taking n.
General form of polynomial.
X power n plus b x
Power
n minus
1.
Yeah.
But in mathematics we use not a, b, c, but a number 1, a number 2, okay, a number 3. And usually we start from a 0. So polynomial, let me denote this as p of x. I can write a0 plus a1 x power 1 plus a2 x power 2 plus, and so on, a number n x power n. General form of a polynomial. Particular case of polynomial, for example, is a linear function, just a0 plus a1x. Next case, a0 plus a1x plus a2x power 2. Then cubic polynomial and so on. Well, what other classes of functions? You can write your answers in chat if you don't have a microphone or maybe some problems with sound.
Have fractions. Functions.
Fraction, yes, it's another example, but it's not so important, and it not will. Yeah, trigonometric functions. Yes, these functions also are very important, and we will use it very often. Trigonometric functions. So the first class is polynomials. The second class is trigonometric functions like sine, cosine, tangent,
Cotangent.
sine x, cosine x, and so on. Trigonometric function.
Yeah.
Another classes of functions, polynomials, trigonometric.
Can you say square function?
Square.
Yeah.
So,
How can you say it? Root function.
well, yes,
It's kind of square too. I think.
logarithmic, right? Logarithmic functions. Yeah, right.
Exponential function.
Of course, logarithm and opposite function exponential.
They are brothers.
Logarithm and exponential function. Logarithm and exponential. Well, there are a lot of other different functions, but I think it's enough for our case. And During our lessons, we will work with exponential functions and logarithms, with trigonometric functions and polynomials. All of these functions are continuous. Maybe in some sense, in some intervals. Logarithm is not continuous when it's includes zero. Maybe some trigonometric functions are discontinuous, tangent, cotangent. But we will consider very simple functions like sine, cosine. Now we review the classes of functions. And what is a derivative? What is a derivative of a function? It's a very, very important question. And this question also related to limit. Yes, it's related with the limits. And of course, if you don't remember the strict definition, I remember it. If you don't remember.
Yes, we can say derivative of a function in a certain point is defined as a limit when x tends to x0 of the difference x of f of x plus delta x minus f of x on delta x.
Delta x, excellent, excellent. Yes, it's a strict definition. The notion of derivative is related with limits. It's related with limits. If we have a function f of x and we consider some point x and some small value delta x, then we can consider the limit when delta x tends to 0, f of x plus delta x minus f of x over delta x. And this new function is called derivative at the point x.
Yeah.
So if this limit exists, this function is called derivative. And for these simple classes of functions, these correspondence with derivatives are known and either more or less simple. Let's start from the last one. That's from the last one. Exponential function. What is the derivative of exponential function? E power x.
It doesn't change.
Right?
Yeah.
The exponential function is a very, very good function from the point of view of mathematics, because the derivative of exponential function, it doesn't change. E power x prime equals to e power x. And the derivative here doesn't change. Logarithm
1 over x.
The derivative of the logarithm is 1 over x. Of course, maybe if you, again, I tell this for all the students, if you don't remember these derivatives, it's not a problem, just type it in Google and you see the table of derivative. Derivative of logarithm is 1 over x. I write here all the derivatives. 1 over x. Logarithm is 1 over x. Derivative of sine is
Cosine
cosine, and cosine
minus
sine. Sine cosine x, cosine minus sinus x. And derivative of a polynomial. If we have a polynomial of degree n,
and
the
1 over n
n minus 1.
and minus 1, yeah.
No, not 1 over n, but n minus 1.
Yeah.
The derivative of a polynomial will be a polynomial of degree
n minus 1.
n minus 1. Let me write it here. E prime x equals to derivative of a constant is 0. So we start from a1 plus here 2a2x, because derivative of x power 2 is 2 plus, and so on, and x power n minus 1. So I can say that derivative of x power n equals to n times x power n minus 1. Well, these formulas you considered on mathematical analysis, and I think it's not a problem to find these formulas if you don't remember it. The next question is what is an integral of a function? Maybe again, I don't ask you about the strict definition, because there are several, in mathematics we consider several types of integrals, but we discuss about maybe the simplest type of the integrals. Integral from a to b f of x dx. Integral from a to b f of x dx.
It's the summation.
Yes, it's related with the summation, and from the geometric point of view, the integral corresponds to rear under the curve.
Exactly.
Rear under the curve. And here I just consider that I just write a final result that integral from a to b f of x dx equals to f of b minus f of a, where f capital of x is so-called anti-derivative. Such function that f of x prime equals to f of x.
May I say that the integral from a to b is the summation of the product f of x times gx on the interval ab?
Yes, it's again we can say also when delta x tends to 0, it's a limit.
Yeah, exactly.
It's a limit. But I show you only the final result that can be derived from this definition, that integral from a to b f of x dx equals to f of b minus f of a, where f capital is such function that f prime x equals to f of x. So here, if we try to compute the integral from sinus, we should use cosine as a. Sorry.
Yeah. If you use cosine.
Minus. We should use with minus, because it's changed the sign. If I use if f small equals to cosine, then
we use sine.
We will use sine, because derivative of sine equals cosine.
Yeah.
And from the geometrical point of view,
It's an area.
yes, it's area under the curve.
Under the function f of x and interval.
We can see the interval from a to b, the function, and the area under the curve. The area under the curve is well, again, we just briefly, very quickly review all the formulas that you study on mathematical analysis, because we will use it in our lessons. For example, we consider how to compute a derivative numerically, how to compute the integral numerically, not applying this formula, but using some numerical techniques. How to approximate complex functions like, for example, exponent or sinus using polynomials and so on.
Yes, we can use the Fourier series.
Not Fourier, but Taylor.
Taylor.
The last question.
Yeah, Taylor, thank you.
The last.
Yeah, Taylor.
The last question, Taylor formula and Taylor series, because Taylor's formula, Taylor's series is also extremely important. Well, I stop sharing just for a minute. Oh, sorry, I don't share, but you don't tell me nothing. I don't share the presentation. I stop sharing the presentation and you don't tell me nothing. Okay, but you see the board. Well, if something will happen with Microsoft Teams, maybe presentation is closed, so tell me this time that this happens and we fix this problem. Well, now I just want to show okay, the next question, the last question that I want to consider with you is related with Taylor's formula. But I see that it's time for the break. I see that it's time for the break, let's have a very brief break between our lessons, just 5 or 10 minutes. And after that we continue and we discuss about the Taylor's series, the Taylor's formula, because this formula is very important. And at the second half of our lesson, we discuss about different types of errors and about the so-called machine error, machine epsilon, the error that is introduced by computer in every computation, every numerical algorithm. Okay, now I stop sharing the screen. I share it again when I come back. Just we have a break for 10 minutes. After that we continue. Oh, I'll come here after 5-10 minutes. Let's have a break. Well, let's continue our lesson. We finish now with the question of the linears. And after that, we discuss about different types of errors in computation. The last and very important thing that we should consider is Taylor's formula. Again, I share the screen, and of course you can type Taylor formula or Taylor's theorem, and you can find the information in Wikipedia and in the book. There are a lot of sources, but let me show maybe the main feature of this theorem. The formula is presented here. There are different forms of the theorem. Here it's written in one form. I write it in your Taylor's formula in maybe a slightly different form. Well, let's consider function f of x that continues, and its derivative continues, and the second derivative continues, and all the derivatives of this function are continuous. So f of x, f prime x, and so on. F power f, the derivative of degree n, are continuous functions.
Did you start recording?
Yes. I don't stop it during the break. It's nothing. And now we can ask the question: can we compute the value of the function at some another point? For example, f of x plus h. So suppose that we have a small step. We can denote this step as h, or we can denote this step as delta x in any notation. But it means that we move from the point x to some small step. Can we compute the value of the function f of x plus h using the value of the function at the point x? And the Taylor's formula gives us the answer: yes, we can. If you look here in this notation, I can write it in this notation. I can write it in my notation. Let's use this one because it's closer to computer and mathematics. F of x plus h equals to f of x plus f prime x times h plus the second derivative at the point x over 2 factorial times h squared plus the third derivative over 3 factorial times HU plus and so on. And sorry, I'm sorry, please call. Hello? Я там второго, наверное, не шел. Согласовать в каком смысле? Это вот тот студент, которого Калинин отказался? Или другой? Просто сейчас, просто писать? Я думаю. Well, the third derivative over 3h plus and so on, and the term n is the derivative of degree n over n factorial times h power n. The formula in Wikipedia is more or less the same. Here it's used a as x and x minus a equals to h. It's a step. It's a difference between these 2 points. But
why did you write x plus h? I didn't understand. Yeah, we have just x there, but you.
Yes, we have x here, but here x minus a, and f of a. It means that here we compute at the point x. Okay, you can substitute here a. If you put here a instead of x, if you put it a, you will have exactly the same result. Here x equals to a.
Okay. I see.
Well, and in mathematics, this series is endless.
Yeah.
This series is endless. And we can use it to find the value of f of x plus h approximately using the first several terms of this series. And we will use this series, we will use this formula in different methods. In the case where we should compute the value of the function at some point using the value of the function at another point. Here we compute the value of the function at the point x plus h using the value of the function, the value of its derivative, second derivative, third derivative at the point and at the point x. And we will use this formula to derive some numerical methods. Please fix it. You can read Wikipedia, or you can find this formula in any other book on computer and mathematics. I'm sorry, I don't say nothing about the books. I can show you the books right now.
I
And I will send you these books by mail too.
So I have a question.
Wait a minute, I open. So here I have two books. The books on numerical analysis, and you can see that the topics of these books, of course here it's hard to see, but I think the students who connect online see it. The topics are more or less the same, corresponds to the topics of our lessons. It starts from mathematical preliminaries, then solution of nonlinear equations, then interpolation, differentiation, integration, initial value formula. So any book of computer mathematics, any book on numerical analysis contains this information. It starts from mathematical preliminaries, then computer mathematics that we discuss right now, solution of nonlinear equations, of some topics, of course, it's complex, it's topics with a star, and so on. Well, I will send you these books. You can read it, or you can use any other book, of course. Well, we consider all mathematical preliminaries, and I think I just show you this slide with these questions, and I ask you to review some features, some points from programming. Loops, arrays, statements, data types, and I repeat that during our lessons we will not write programs at every lesson. Maybe I ask you to write programs for simple algorithms, but you should review it.
C++.
In C++, yes, you can use C, C++, you can use Python, Java, any language that you want. Any language that you want. Of course, I can write here, C++. C++ doesn't matter. It doesn't matter. Well, it's enough that you will review the main topics. For, while, do while statements, input output, arrays, and so on. I will not consider it for today because in different language these statements are more or less the same, but it differs. And I repeat again that you can use any language that you want. But what I want to consider with you today, very briefly, as an introduction. Well, what I ask you, what we consider today, is some features of computer arithmetics, finite-digit arithmetics. Because the computer arithmetic is a source of errors, is a source of mistakes. Well, 3 questions. what is the value of 2 plus 2? Of course, you told me that 2 plus 2 is 4. And if I write a program, and if I run it, the program outputs me the result that 2 plus 2 is 4. The next question is, what is 3 over 2? 3 over 2 is 1.5. And the program, if I implement this division in the program, also outputs me the result that 3 over 2 is 1.5. But what is square root of 3? Square root of 3 is not a rational number. Square root of 3 is a so-called algebraic number. And in mathematics, if I write it with pen and paper, square root of 3 raised in square gives us the result 3. But if I run a program, the result will not 3, but 3 with some error, 3 with some mistake. It's not exact because square root of 3 is not integer, is not rational, is irrational number that can be represented exactly with the infinite number of digits after decimal point.
Okay.
If I just compute square root of 3, where is, oh, it's, you should maybe not this one. Yeah. Square root of 3 has an endless number of digits. Endless number of digits. And the exact answer, square root of 3 raised in square, gives us 3 only if we take infinitely many numbers after decimal point. But in computer, we have only fixed number of digits after the decimal point. That's why square root of 3 raised in square,
It will be 2 something.
2,99999 or 3.0000000 and 1 something. No, we will never get 3. It depends on that, and also it depends on the storage structure of numbers in computer. We will discuss very briefly about it on programming, and also I review some main points here, just at 5 minutes, because it's not the main topic of computer mathematics, but it's very important to understand it, that every number that we write here as a decimal number is stored in computer in binary form, in binary system of notation. In this case, even very simple numbers, such, for example, 0.1 in decimal system of notation, it cannot be written in binary system of notation exactly, because this number in binary system is written with infinity many number of digits after decimal, after the point. a very simple number, for example, 0.3. 0.3 is also cannot be written in binary system with a finite number of binary numbers. 0.5 can be written. Well, I just want to stress that there are a lot of numbers that are very simple from the first point of view, but it cannot be represented in computer with finite number of digits. Maybe it becomes even in a decimal system of notation, like square root, or it may come from this transformation from decimal to binary. But in any case, there are a lot of numbers that cannot be represented in computer exactly. That's why we have some mistakes. So I skip this theorem about general position scheme, and I show you this slide that any number in computer is represented in so-called normalized scientific notation. Any number. I consider it in decimal system of notation because in binary is more or less the same. The problems are more or less the same. Well, the number is represented in the following form. Some coefficient R, let me open full screen, some coefficient times 10 power n, where n is integer, it can be positive, it can be negative. R is a real, between, it can be between 0.1 and 1. It can be more usual, I can write that R is between 1 and 10. In decimal, it's greater than 1 and smaller than 10. Smaller than 10. And n is an integer number. So using this form of notation, I can write in a short form very large numbers when n is large, and very small numbers when n is a negative number. And exactly the same for binary numbers. This coefficient is called mantissa, and the power is called exponential part. Even in binary, we use 2 power m, not 10 power m. And in computer, the real number is stored more or less like this. It's a single precision real value. This single precision value requires 4 bytes for storing. 4 bytes corresponds to 32 bits. And these 32 bits are divided into several parts. 1 bit for the sign of number that corresponds to sign of mantissa. 0 for positive, 1 for negative. It doesn't matter. Of course, you should remember that 1 bit for the sign, 1 bit for the sign of the exponent, Then 7 bits for the exponent and 23 bits for mantissa. So for the single precision real value, any real number can be stored with a precision not greater than 23 binary digits. Yes, 23 bits. These 23 bits, 23 binary digits, corresponds to 7 decimal digits after the point. When we work with a single precision real value, the precision is not greater than 7 digits after decimal point. When we work with double precision real value, the size for mantissa, for exponential part, is another. I don't remember. Yes, I write it here. No, it's not written. But of course, you should not remember these values exactly. But you should remember that the double value requires 8 bytes, and with the use of double precision, we can store the real number with 15, 16 digits after decimal point. 15 or 16 digits, not greater. So we cannot store a number, for example, pi 3.1415 and infinity many numbers. We cannot store it with more than 16 digits after decimal point. That's why any operation in computer produces this small mistake, this small error that is called machine error. And the first question is how to find this error, how to estimate this error. To do it, we can find so-called machine epsilon. What is a machine? We can consider such two numbers. For example, number x has a data type float, single precision value. Then we can consider some another number, delta, and we can find x plus delta or x minus delta. But when the delta is very small, then x will be equal to x plus delta. When delta is between 0 and some small positive number epsilon that equals to 2 power 1 minus n. In real mathematics, when we use pen and paper, x will equals to x plus delta only in the case when delta equals to 0. X plus 0 equals to x. But in computer mathematics, I can take small positive number, delta, find x plus delta, and the result will be equals to x. The number epsilon here is called a round-off error and is a characteristic of the particular computer, of the operating system, of a mode of compilation, of a mode of computations on computer, single or double precision. Well, and the first task that I ask you to solve, I ask you to solve it as a home task, the homework.
Professor,
To write a program to evaluate the machine epsilon, machine epsilon. How to do it? How to do it? The idea is as follows. The idea of the algorithm that helps us to evaluate the machine epsilon is as follows. Let's consider this epsilon in a form of 2 power minus k. Let's take epsilon equals to 2 power minus k, where k is some integer number. Then we can check the condition. If epsilon equals to, sorry, not epsilon, it's written here, of course, not epsilon, but 1, real 1.0 equals to 1.0 plus epsilon. So, if it's true, then we find the machine epsilon. If it's not true, then we should decrease this epsilon, or other case we can increase k. So if it's not true, so if 1 doesn't equal to 1 plus epsilon, we should increase k and recompute the epsilon.
please, sir. I didn't understand very well the machine epsilon. Possible to explain, please?
Machine epsilon. Yeah, it's such number, such small number, that we take this number and 1 plus this number gives us 1. This is the meaning of machine epsilon.
1 plus epsilon gives 1.
Yes, 1 plus epsilon equals to 1. Because it's a computer, it's a machine. It cannot represent small numbers. It cannot operate with very small, very small numbers, because it has only 15 digits after decimal point. 15. So in real mathematics, on pen and paper, 1 plus epsilon never equals to 1.
Yeah.
But in computer, 1 plus epsilon sometimes equals to 1. Of course, if epsilon equals to 0.5, 1 plus 0.5 doesn't equals to 1. Well, look to this algorithm. This is the algorithm is written on pseudocode.
Pseudocode. Yeah.
Pseudocode.
Yeah, pseudocode.
Very simple algorithm. You can implement it on any computer language.
Yeah.
We start from this. Let assign epsilon to 1 and k to 0. While 1 plus epsilon is not equal to 1, we divide epsilon over 2 and increase k. How it will work? What will be the first comparison? Epsilon equals to 1. 1 plus 1 equals 2 in the computer. 2, is it equals to 1? No, we divide epsilon over 2, and epsilon becomes 0.5. Then 1 plus 0.5, 1.1. Is it equals to 1? No, and we divide it over 2. And so on. We decrease epsilon, and after several steps, epsilon will be such small number that
will be equal 1.
1 will be equals to 1, and this loop will terminate.
Yeah.
This loop will terminate.
So it means that epsilon, we choose it. It's not a specific number.
It's a, no. Epsilon depends on the computer, on the data type.
Okay, so we have to find
Yes.
the epsilon
Yes.
of our system.
Yes, yes, yes.
Okay, I got you now.
Yes. Right. The task is to write this simple algorithm and to output the epsilon and k
Of our
on your computer.
Yeah.
Your computer, your programming language, because the epsilon may differ. It can be different for different programming languages.
Yeah, please, sir. But why there you say epsilon equal to power minus k?
But
here,
epsilon over 2, it will be the same.
now epsilon there it's 1.0. Here epsilon have another value.
Okay. It's not another value because k equals to 0. When k initial value of k is 0,
epsilon equal 1.
Epsilon equal 1.
Okay. So it means that the formula of epsilon is 2 power minus k.
Yes, 2 power minus k, and we decrease there.
Yeah, until we'll reach the step where we'll have 1.
Well, this is the first task as a homework. Please implement this algorithm and
Java,
next any language and find the machine upside. Okay. Now let's discuss again about the errors. You see here that we write some program. When we write some program, any algorithm, any program that computes operate with real numbers, it includes some error, some machine epsilon. Also, when we have a deal with some real data, with some real numbers, some values, some real world information, this information also can contain some mistakes, some errors. For example, if I ask you, what is the temperature now? You can tell me it may be -2, -3 degrees below. It's 2 or 3 degrees below 0. It's not very precise value. It's a value with some mistake. Because when you measure your when you are you and you measure your temperature, the result of this information is more precise. Because you measure, oh, the temperature is 38 degrees, I'm ill. My temperature is 36.6, I'm fine. So the result of measurement are more precise. So the precision of numbers, precision of values is very important. And in computer mathematics, we consider some different type of errors. And usually we consider two main types of errors. Absolute error and relative error. The definitions are given here. Suppose that P is a real value. P can be, for example, a real value of a temperature right now. And P1 is approximation, our approximation of this real value. In this case, absolute error is just a module of a difference between P and P1. Is just a module P minus P1. Or even P1 minus P, it doesn't matter because it's a module. So it's just a difference. And relative error, so this is error and relative error. Let me denote just E and P, E and R. Relative error is P minus P1 over P. From the source point of view, it's the same. I just divide it over, I just take this difference and divide over P. So I can write that R equals to P over module P. Yeah. But the relative error, when P is not zero, is more good. It's a better indicator of error in comparison with just absolute error. Let's consider some examples. Let's consider some examples. Example number one. Suppose that we have a real value x, 3.15, 141592. Suppose that it's a real value, and our approximation is x1 3.14. X is a real value, x1 is approximation. How to find absolute and relative error? Absolute error is just a difference, and it equals to 0.001 and something. Relative error, E over X, and in this case it equals to, or sorry, I should write here one more 0, like this. It equals to 0.0005. Well, when the numbers are approximately equals to 1, between 1 and 10, it doesn't matter what error to use, absolute and or relative. But let's consider another case. Suppose that the values are very large. Suppose that the real value, true value is 1 million, and our approximation is 999,996. How to compute the error? It's just a difference. What is the value of the difference here? Why 0, 0? Difference between these two numbers. Oh, 0, we don't write, just 4. Yes? Yeah, 4. The value is 4. Yeah. From the first point of view, the error is large. But if we consider relative error will be small because the values are large. So if we measure very, very large value with some mistake, this error, absolute error, may be significantly large, but the relative error is small.
So it's better to use relative.
Yes. Let's consider the example number C. Suppose that the real value z equals to 0.000012 and our approximation z1 equals to 0.000009. All the values are small. The absolute error, if we compute as a difference z minus z1, equals to very, very small value, 0.0003. But if we compute the relative error will be significantly large, 0.25. It will be much more greater than relative error in the second case. So, if the true value, if p moves away from 1, it means that p is significantly larger or significantly smaller than 1. In this case, relative error is a better indicator of accuracy. And related with computer mathematics, relative error is preferred because all the numbers are represented with a floating point representation. And it deals with mantis of the number. So the relative error is a better indicator. Well, please remember these two types of errors: relative error and exercise. I will send you this presentation after the lesson. I will send you this presentation. Please solve not all of the exercises, but some of the. For example, the exercise 5 under the letters A, B, and C. Exercise 4, letter A. Exercise 3, letter A. Not all, because these exercises are more or less the same. Well, now we have half an hour. Let's consider and let's discuss about these first two exercises. And let's try to solve it. Because on the next lesson, we will consider some methods which will be related with this exercise. Find the intervals containing solutions to the following equations. And this is the first equation: x minus 3 power minus x equals to 0. So we consider this equation. This equation is not linear, not polynomial equation, not quadratic equation. For quadratic equation, you know the formula, how to find the root of equation. This equation, we don't know the formula. And in this exercise, I don't ask you about the root of this equation, but I ask you about the interval that contains this root, interval that contains solution. So you should tell me the interval the interval from A to B, for example, that contains the solution of this equation. Can you guess what is the idea? How to find the interval that contains the solution of this equation?
At least to rewrite the equation and to say, for example, that x will be equal to 3 power minus x, and to try to guess the equal value in order to see.
No, your idea is not correct, because it's very hard to guess when x equals to 3 minus x, 3 power minus. No, nobody can guess, but we can guess, and we can find the interval between A and B. It will be this point, the point when x equals to 3 power minus x. Well, do you have any ideas how we can find the interval that contains the root of this equation?
Minus 1 to 1. Minus 1 to 1.
Why? Why not maybe from 1 to 2 or 1 to 3 or 4 to 7? Why?
Here I put 0. 0. Yeah. It's like we will get 1 over 3 power x. If I put 0, it means that we have 1 here. So 1 minus 1 equals 0. It's not correct.
Well, also, if we consider this problem in general, this is some function, yes, f of x equals to 0, right?
Yeah.
F of x equals to x minus 3 power minus x. And we should estimate a point at which f of x equals to 0. Suppose this point is here. Yeah? Right? But if we suppose also that this function is continuous, we discussed about continuous functions in the first half of the lesson. It means that, for example, this point, this function will be positive, and at this point, this function will be negative. Something like this. Yeah? Different signs, plus and minus. Or, in another case, plus and minus. But different signs. If the function has different signs at the end point of the interval, and the function is continuous without jumps, it cannot jump through the 0. It should intersect the 0, and this point will be the root of the equation. If the function at this point has negative, minus, this point plus, between these 2 points, it must be the root of the equation. Because the function is continuous. This is the main idea. And for this particular case, it's very simple to find such points. Just look to the function and substitute, for example, let's substitute x equals to 0. What happens when we take x equals to 0? 0 minus 3 power 0. What is 3 power 0? 1. And we have f of x equals to minus 1, negative. The sign is minus. Let's take, for example, x equals to 1. F of x is 1 minus 1 over 3. Plus. So if I take 0 and 1, at the point 0, the function equals to minus 1. At the point 1, the function equals to 2 over 3. And I decide that between 0 and 1, it must be a root of the equation x minus 3 power minus x equals to 0. So the answer to this question is very simple. We should find such 2 points where a function has different signs. Between these 2 points, it must be a 0. If the function is continuous, because if the function is discontinuous, it can jump. So it can look like this. Here and here, discontinuous function. No rules.
Can we say that this function is not polynomial?
It's not a polynomial.
So how can we know that it's continuous then?
Because here it's like exponential function.
Yeah.
It's
8
8 power x.
Power x, yeah.
It's continuous.
It's like we have a polynomial function plus export function, which is a continuous function.
Well, we solve task number 1, letter A. Try to solve letter B and letter exercise number 2. Exercise number 2. There are three examples, A, B, and C. You can solve just one of them to understand how it works.
It's homework task 2.
It's the exercise for the next week. I will send you this presentation by. I will send you also the link to the video. I will send you the books. Where you can read about it. Okay. Well, that's all for today. Do you have any questions?
No.
Well,
if it's possible just to have the book and the
course. Yes, I send you. I will send. Well, next week we will have a lesson at the same time. We will have the lesson at the same mode, mixed mode. If somebody are here in Nizhny Novgorod, I ask you to come here in this room 420, building 2. If you are not in Russian, of course, connect to our meeting online.
So it means that next time the course